Thanks. I'll begin with a word of prayer. Dearly Father, we thank you for this day again, Lord. I thank you for the students. I pray that you guide our steps today. Help us to glorify you in what we do, Lord. In your name I pray. Amen. Okay, so something I should mention. So this is a circle of ideas that I have failed to communicate to you guys, but maybe we've touched on them. I'm not sure, but this is a theorem. If we have the limit as n goes to infinity of a sub n, if it's equal to L, then this sequence is bounded. All right? And so, like, the proof of that, it's fairly easy to understand. So, you know, suppose L looks like this. Suppose here we look at y equals to L, you know. And then, so what does it mean to say that the limit as n goes to infinity of a sub n is equal to L? What does that mean? It means we can make a sub n minus L less than epsilon, right? For any epsilon we pick, right? Provided we take n far enough out. So in particular, you could say, I don't know, let's put epsilon equal to 1. Right? If I put this as equal to 1, then the limit existing, right, that means that there's some kind of m, say here, where beyond that point, let's see here. So what does epsilon plus, or what's L plus or minus 1 look like? You know, those are horizontal lines, right? So here's like L plus epsilon, L minus epsilon, which in this case is L plus 1, L minus 1, right? So supposing that the limit exists, that means I can pick an m, right, such that beyond that m, any of the points in the sequence, they have to fall within that band, right? They have to fall within that band. And then, like, what happens before m, I don't know, all kinds of crazy stuff could happen, right? You could have sequence members wherever. But the point is, you got this set of values, a1, a2, dot, 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 am, right? And then you've got stuff, the rest of it, right? All this, right? So these are within, basically these are in L minus 1 to L plus 1. They're in there somewhere, right? And over here, you've got a finite set of values. So what's the minimum? So you could take, okay, so let me call this thing Pac-Man. So we could take the minimum of Pac-Man and, you know, L minus 1. That's going to be less than or equal to an, which is going to be greater than or equal, which is going to be the maximum of the stuff in Pac-Man and L plus 1, right? Those are bounds for the sequence. The sequence has to be stuck between those two things. So any convergent sequence is bounded. So, like, that's great. In fact, if we have a monotonic sequence, then we know that it will converge to the least upper bound or the greatest lower bound, depending on whether it's increasing or decreasing, if you look in the other book. But what's perhaps even more useful than this is if the sequence is unbounded, right? That means it doesn't its limit doesn't exist, right? So like a mirror theorem. If you have an unbounded sequence, then the limit as n goes to infinity of a sub n does not exist. Which means, for example, this, close cousin to that, means that the limit as n goes to infinity of an is not equal to 0, right? which means that the series a sub n diverges. Right? So if you can show that the terms in a sequence are unbounded, it follows that the nth, you can use the nth term test to show that that series diverges. Now the reason I'm talking about this is an example that I'm not sure if I really hit on in its full glory. It would be something like this. The sum n equals, say, 1 to infinity of n factorial over, let's say, 3 to the n. So my intuition here is that a sub n, which is n factorial over 3 to the n, goes to infinity as n goes to infinity, right? This is intuition. But we can do better than intuition, all right? Let me give you an argument for it. What's an argument? Let me actually try to show it to you more carefully. So here we have, let's say for n greater than or equal to, I think if I put 5, it's good. Anyway, here's a sub n. This isn't using that yet, but this is what? This is n factorial over 3 to the n, which is actually equal to n times n minus 1 times n minus 2, 3 times 2 times 1. Let me do 4 times 3 times 2 times 1. All right. And then downstairs, what do we got? We've got 3 times 3 times 3 times 3 times 3 times 3 times 3. All right. This is what 3 to the n means. N-fold factors of 3, n-fold factors of n, n minus 1, n minus 2, and so forth. So my intuition is basically based on the idea that at some point the terms in n factorial are bigger than the terms in 3 to the n, right? So the game I'm going to play here is for n greater than or equal to 5, I think I can peel off, let's see here, this piece right here perhaps. So n greater than or equal to 5, if n equals 5, what's this? Let me just expand. N equals 5, what's this boxed term look like? This is just 5 times 4, right? If n equals 6, the thing that I boxed is what? It's 5 times, excuse me, oh, did I do the right? Actually, I'm sorry, I'm an idiot. If n equals 5, the thing that I boxed is actually, it's actually just the number 4. That's what that notation means. Because this is going from n minus 1 to 4. In the case n equals to 5, all of these terms are just the 4 at the end. All right? When we get to 6, what's in the red box would be 5 times 4. When we get to 7, what's in the box would be 6 times 5 times 4. All right? And that's why I need to assume that n is greater than or equal to 5 so that what's in the box makes sense. All right? Yep.
So what would happen if you set n equal to 4? It wouldn't work?
Then I'd have to have a different argument. I'm only going to look at n greater than or equal to 5.
Is there any reason why you picked 5?
I worked this problem for 2 to the n earlier today, and picking 4 worked nice. So yeah, experience is the short answer to that. But this is, what is this? This is greater than or equal to what? You see what these are? These are what? I can make these 3, right? If I make everything in the red box 3, then I'm clearly making what? Am I making the fraction smaller? Yeah, I've replaced let me just emphasize the red box part. Of course, you can cancel, right? What is this actually equal to then? This is actually equal to, I mean, technically this would be, if you want, this is actually 3 to the n minus what? How many copies of 3 do I have in there? All but 4, right? This is 3 to the n minus 4. So those will cancel with this piece down here, right? And I'm just left with 3 times 2 times n divided by 3 times 3 times 3 times 3. Cancel the 3's, right? So we get 2n over 27. Why did I do that? Why am I doing this? Well, pretty simple. Now, what can we say about this? This definitely goes to infinity, right? As n goes to infinity, right? Hence, 0, right? 0 is less than an, which is less than 2n over 27. I'm sorry, I'm an idiot. Let's flip that around, right? What did I show? I showed that a to the n is greater than that. So I have 2n over 27. That goes first, right? And then an is above that. This implies what? Which then implies what? So this is that the limit as n goes to infinity of a sub n is not equal to 0. Therefore, the sum n factorial over 3 to the n diverges by the nth term test, right? Why is it not immediately obvious that the limit of an as n goes to infinity is not 0? I would argue it's not immediately obvious because the initial limit, what kind of limit is this? I mean, what kind of term is this? This isn't something that's going to infinity or something that's going to infinity, right? So to be careful, some kind of argument has to be given to prove that this actually doesn't limit to 0 or something else, right? And this is the kind of argument that affirms my intuition that it went to 0. Yeah.
So a factorial is greater is that function, the factorial function is going to be larger than 3 to the n or x to the n or whatever.
Yeah, I mean, I think we could it's pretty clear we could recreate this argument for 7 to the n or 10 to the n or whatever, but then we're going to kind of have to pick a different, we're going to have to keep more terms on the edges. Like for the problem in your homework, you've got you got n factorial over 2 to the n in the homework. So for that one, you just need to keep maybe you can use n greater than or equal to 4 or 3 or something like that. I may be able to make this argument still go with n greater than or equal to 4, but who cares? Pick it big enough so you don't have to worry about it. If you can show that the inequality is met for terms eventually in the sequence, that suffices to show that the limit's unbounded. I don't have to show that the inequality holds for all n. What I need to show is that eventually the sequence is bigger than one that diverges. If you can show eventually your sequence is bigger than one that diverges, then the sequence diverges. So anyway, I thought this was an example that was kind of missing from our, lexicon of examples or whatever. Yeah. Sure.
How'd you get 3 to n minus 4 from there?
Well, process of elimination, there's n factors here, and there's 4 things left out, so that must be 3 times n to the n minus 4.
The red box, how you got. But I kind of figured it out.
Why did I pick that?
went from n minus 1 times n minus 2 dot 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 4 to 3 dot 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 3.
Why didn't I make it go to 3?
No, like from that red box to the red box adjacent to it.
Well, the thing is, if n is greater than 5, right? It looks like this at n equals to 5. It looks like this at n equals to 6. It looks like this at n equals to 7. The terms inside the red box, every one of them is larger than 3. So, in fact, this is actually, to make this strict, I mean, each one of these numbers is greater than 3. So I can replace those with 3s. The reason I'm doing that is because then I can cancel them out here for arbitrary n, which leaves me something that I can easily see that the limit is, there's no end, and this step right here is canceling the infinity in some sense. Like this is going to infinity, that's going to infinity, but it's the same, so it cancels, and it leaves you with this, which shows you without a doubt that the numerator wins. If the n factorial was downstairs, a similar argument could be given to show that the limit of a sub n is 0, which would then be useless because as it regards to the convergence of the series, because if we can show the limit of a sub n is 0, it doesn't show the series converges, it just shows it might converge. If you flip this over, then we'd use the ratio test to check convergence. So you guys have questions? That's all I got in terms of what I felt like I needed to tell you today. Yes, Josh?
Section 9.1, number 89.
9.1, number 89. Oh, this one. Can we ask a different one?
The question with number 86, part C.
86, I'd also rather not talk about 86.
We've been through these.
You have picked the two that I know I'm stumped on at the moment. Not that they're impossible, it's just we should talk about every other homework problem before those two. Is what it boils down to, okay?
83.
Of section 9.1? Oh yeah, that one we can do.
Okay.
Although, again, this is not the optimal homework question to talk about. You got others? I'll start down I tell you what, we'll start here, and if we get tired of it, we'll bail. Number 83. But the ones they just asked me about, section number 86 and number 89, those are proof questions. They actually require some thought. And I probably shouldn't do them in class, honestly. I know right now that if I try, I won't be able to today. I just know where my mind is. So here's the Fibonacci sequence according to your book. A1 equals to 1, A2 equals to 1, and AN plus 2 equal to, what is it, AN plus AN minus 1, right? We talked about this some other day. And what am I supposed to do? I'm supposed to find the first 12 terms of the sequence. All right, so what is the first 12 terms of the sequence that we can do? 1, 1, 2, 3, 5, 8, 13, 21, 34, 50, 55, 89. How many do I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, one more. 144? Cool. So that's part A. Fine. We can all do that. And then part B, we're supposed to define Bn AN plus 1 over AN, right? And we're supposed to write the first 10 terms of that sequence. What are the first 10 terms of this one? So we get what? 1 over 1, 2 over 1, 3 over, I can't do math. Let's see. That over that, that over that, that over that, 3 over 2, 5 over 3, 8 over 5, where was I? 13 over 8, 21 over 13. If I haven't skipped one, it'll be amazing. 34 over 21, 55 over 34, and 89 over 55, and so forth. All right, great. So this is a, yes?
Well, my question is really, I get.
You get that part,
Well,
yeah.
with the sequence you defining here is a to the n plus 2 is equal to n plus a n plus 1. That a n plus 2, is that supposed to mean anything? Because I don't see, because the Fibonacci sequence.
So for example, a sub 1 plus 2, which is a3, right?
Yeah.
How is that defined to be? That's defined to be a 1 plus, I'm sorry, idiot. So 1, dang it.
Would be a sub 1 plus a sub 0, right?
Yeah, I'm thinking of this the wrong way. That's supposed to be n plus 1. That would make more sense. So this is 1 plus a1 plus 2 is a1 plus a2. Yeah. Is this an minus 1? Or did I just made that up? Oh, it's plus 1 in the book. I'm an idiot. Yeah, that minus was just my transcription error on the board. It's dumb. Sorry about that. Obviously, I was using this to create that list, obviously. And then part C, what is it? What are we supposed to do for part C? Did I answer your question, Josh? I'm not sure.
Yeah.
So we're supposed to show that Bn is 1 plus 1 over Bn minus 1. Can we do that? How would we?
It says that you're supposed to use the equation for part D, that dn equals an a of n.
Right. The Bn is still defined by the successive ratio of successive terms in the Fibonacci. Let's see here. This is the same as. Let's just restate this equality in terms of the a sub n's. So b sub n is what? It's an plus 1 over what? Over an equal to 1 plus, what's that? 1 over what? Bn minus 1 is what? That's an over an plus 1? Or n minus 1, yeah. I can do this because, by the way, nothing is 0 here, right? So there's no danger of these divisions. What's that? That's the same as an plus 1 equals to an plus an minus 1 times an over an, which is the same as an plus 1 equals to an plus an minus 1, which is exactly the definition of the Fibonacci sequence restated instead of n plus 2, n plus 1. I mean, this is the definition of Fibonacci for n greater than or equal to 2, which we assumed up here, right? I think. Did we? Maybe not. No, n greater than or equal to 1, sorry. Huh. Well, n greater than or equal to 1. Let's see here. To be careful, if I'm writing this, what am I assuming? What's assumed? Assumes what? For Bn minus 1 to make sense, we don't have a B sub 0, right? So this equation only reasonable if n is greater than or equal to 2, which is good because we also need n greater than or equal to 2 here to fit in with my Fibonacci, which starts at 1 in this problem. But you can reverse this chain of equivalence because I can go from here to here to here, which gets me back to there again. So it's just a restatement of the definition, the recursive definition of Fibonacci.
Wait, so how is that related? Because it's not exactly the same as the Fibonacci sequence, right?
And you see if n is greater than or equal to 2, so j is what? J is equal to n minus 1, right? Which is greater than or equal to what? 1. There you go. I mean, that's literally what's giving it at the start of the problem. I've changed the j to, I mean, it's with j instead of n, but it's the same, logically it's the same thing, right? I mean, you got to free your mind of n having a fixed but separate meaning. N is just a placeholder for a relationship. D, we're supposed to show the golden ratio. Ooh. Can be defined by the limit as n goes to infinity b sub n, right? Let's see here, limit as n goes to infinity of b sub n, right, is equal to the limit. Now, can you explain why the limit should exist? Why, what does this equation right here show you about this sequence b sub n? This is actually a non-trivial application of the monotonic sequence theorem. See, because what this formula says, since that's positive, that says that b sub n is always being, as it relates to, what's the relation of bn and bn minus 1? Is it, stink, how can I say this? Well, you can see over here that bn is a what? It's an increasing sequence, right? And you can also see that it's bounded above by what? It's fairly obvious it's bounded above by 2, right? Now we could try to prove that. I will spare you those details, but you could prove it's bounded above by 2. And what that means by the bounded monotonic sequence theorem is that the limit of b sub n exists. So this exists, call it beta, right? So by limit laws, this goes to 1 plus 1 over beta, and then you can solve for beta. So you got beta, 1 over, 1 plus 1 over beta, right? Multiplied by beta, we get beta squared equal to beta plus 1, which is beta squared minus beta minus 1 equal to 0, which gives me solution beta is equal to 1 plus or minus the square root of, what is it, 1 plus 4 over 2. Beta being positive, choose the plus. So we get 1 plus root 5 over 2. Also known as what? The golden ratio, yes. This problem's rich. It's here. There you go. I like it, though, because it actually gives us a chance to appreciate where the monotonic sequence is most powerfully used, is when you can't actually find an explicit formula for something, and yet you can see that it's increasing and bounded above. Monotonic sequence theorem says limit exists. And sometimes knowing the limit exists is enough, paired together with algebra, to find it. Nowhere have I written an explicit formula for Bn. Right? It's kind of neat. So the other thing this says is that the ratio of successive terms in the Fibonacci sequence tends to this value, 1 plus root 5 over 2. It is, yeah.
So like things can be bounded by an irrational number.
We can have sequences of rational numbers whose limits are irrational. Absolutely. For example, you can take a circle and you can like inscribe it with, you can inscribe some shapes inside it that are inscribed in the circle and keep taking more and more line segments, getting closer and closer. And you can take the limit as the number of sides of those approximating polygons get closer and closer to the circle. The perimeter of that polygon divided by the diameter of the circle limits to pi. Even though every perimeter will be, oh, that's not true. The distance between those points doesn't have to be rational. But I suppose you could inscribe it with rational, well, let's not get crazy anyway. There are lots of rational sequences which limit to irrational things. That's not the greatest example. That's a good example. We had this one, right? This sequence, 1 plus 1/4, 1 plus 1/4 plus 1/9, and so forth, This thing has limit, well, let's call the nth term in here Sn, right? We know the limit as n goes to infinity of Sn. I told you guys the other day it's what? No. That's another good example, though. If I let Tn 1 minus a half plus a third minus a fourth plus dot, 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 then you're right, Tn goes to natural log of 2, which of course is irrational as n goes to infinity. This one I was looking, this is another token example. This is the p equals 2 series. That's the partial sum for the 1 plus a half plus a ninth plus the limit of the partial sums goes to pi squared over 6. But the larger point I'm making here is every partial sum is a rational number, every single last stupid one, yet the limit is irrational. That's an irrational number. That's also irrational. You can't write natural log of 2 as the ratio of two integers. It's not a rational number. In fact, every irrational number can be attained as the limit of a sequence of rational numbers. Every irrational number has this form. In fact, that's how you can construct irrational numbers if I was going to be truthful with you. Say, how do you build irrational numbers? As limits of rational numbers. That's actually how you do it. But now I'm getting quite a bit beyond the course, so I should stop. You must have other homework. So someone asked me a homework question, which is lower level, please. 8.8 number. 8.8 number 84. All right. This is your idea of a lower level problem. You guys are killing me. Let's see here. Section 8.8. So f is the integral from 0 to infinity g m delta dx over a plus x quantity squared, where g is the gravitational constant. We're supposed to find f. So he says, now the setup for here, we're talking about a semi-infinite uniform rod that occupies the negative x-axis. So here's the picture. Right, so if you, 0, 0. If you look over here at a point which is distance x, right, then, actually I should call that distance a, I think. picture backwards. I'm sorry, guys. I can't read. He says non-negative, not negative. Not negative, not negative. I was about to get really, really confused. So he says the semi-infinite rod is over here, all right? And he puts a particle at minus a comma 0 with mass m. Now this rod has, if you look at a little dx, then delta is the mass density. It's the mass per unit length. So dm would actually be equal to delta dx. And so if you wanted to find the gravitational force over here due to just that little bit, just this little bit dm, what would the gravitational force be? See, df would be, by Newton's universal law of gravitation, g, big mass, little mass dm, divided by the distance squared. And it's a force of attraction, right? So it would be pointing at the gravity. Force of gravity would be like this, right? So the sign is right. I don't need a minus because that semi-infinite rod is going to pull the mass m towards it. And so this distance, if this distance is x and this distance is a, right? A, we're taking a to be positive, then we have a plus x quantity squared. So that's the force that's generated from just one little bit of mass on the semi-infinite rod. So where's this formula that you're given? What's this? This just says if you want to find the net force of gravitation on the mass big M due to the semi-infinite rod, we just integrate from 0 to infinity. That takes the sum of all the forces from the infinite rod. That's where that formula comes from. The book doesn't tell you this, but I thought it'd be good to derive it, right? This doesn't really help you do the homework problem, does it? No. The homework problem is simpler than that, though. This is the sort of thing I would expect you to show in Physics 231. So this is defined to be the limit, right, as t goes to infinity of the integral from 0 to t of g m delta dx over a plus x quantity squared. What's that integral? That is minus g m delta over a plus x evaluated from 0 to t. G, m, delta, a, all constants. This is just a 1 over x squared integral, basically. Integral of stuff dx over a plus x quantity squared is that stuff, right, times the integral of du over u squared if I set u equal to x plus a, which just is minus 1 over u. So that's why you minus 1 over that. That's it. And then limit as t goes to infinity. What do we got? We got minus g m delta over t plus a plus g m delta over a plus 0. What happens as t goes to infinity to the first piece? It goes to 0. And the second piece? Yeah, so we get gm delta over a. There you go. I'm sorry, I seem to have worked your homework problem, but no one usually complains when I do that, yeah. Now, this speaks to a general pattern we see in physics. When you find forces, like, it's interesting, right? Like the force of gravity from a point particle to another one is depending on the reciprocal, whereas the force of gravity from this infinitely extended mass depends on just the reciprocal of the distance. Kind of pattern you see in physics again and again. Anyway, other questions? Or is there something you want to ask me about that one? Or 8.8, number 80? So I assume you've already shown it's a probability density function, right? I'll just do part B then. So for part A, what should you do? You need to show that the integral from minus infinity to infinity of f of t dt is equal to 1. So I'll let you work that out, all right? For part B, we're supposed to calculate the probability for x being between 0 and 4. All right? So the way that's done is you just integrate from 0 to 4, t f of t dt. Oh, I'm sorry, not even that. There's no t. This would be the expectation. Sorry. It's just f of t dt. Now, let's see here. In number 80, you're given, what is the formula for f of t between 0 and 4? From the book, we see that that's equal to the integral from 0 to 4 of 2/5, right? E to the minus 2t over 5 dt. By the way, starting tomorrow, I am only taking homework questions from chapter 9. And more specifically, I will insist on taking questions from sections 9.2 and beyond. So, because we're not getting where we need to be here, example-wise. That's fine, but I'll fix it tomorrow. Okay, so then what? So you do the integral. Yeah. So that's 2/5 times minus 5/2 e to the minus 2/5 t evaluated from 0 to 4. So that's minus e to the minus 2 over 5 times 4 minus 1, I suppose, whatever that is. Anyway, let me not even write that down. You guys can work that out, yeah? You not even write that down. You guys can do that. What's meant by part C there? Part C, it says define E of x, right? So part C, you're supposed to find E of x, which is by definition the integral from infinity to minus infinity to infinity of t f of t dt, right? Which means that you have to actually calculate the integral from 0 to infinity, right, of 2/5 t e to the minus 2t over 5. Where did the integral from minus infinity to 0 go? Remember, f of t, I haven't written it down, but in the problem it's given to you that f of t is 0 for t negative.
You asked, where did the negative infinity to 0, where did the negative infinity go?
Yeah.
Isn't the graph for E of x, doesn't include negative infinity?
Oh, but e of x is not, it's not a known function. This means the expectation of x relative to the probability density, little f. I mean, it's in the right before number 80, right above number 80, there's a couple definitions given, and it's using those definitions. This is so-called expectation value of x, which is something from statistics, given probability density little f. But then you can do this integral, right? You have to integrate by parts, you take the limit, and so forth and so on. Other questions? Mm-hmm. 9.1, number 38. That sounds promising. Aha, yes. this Fibonacci one we looked at today, that's an interesting problem. A lot of people see this golden ratio and the interplay between the Fibonacci sequence and geometrically pleasing rectangles and the log spiral and all that stuff as evidence for beauty in mathematics, which of course points to the glory of God. I think they're interesting arguments. I don't know how much weight those really have, but they're pretty. 65.
You said you're not doing two of them.
I'm sorry?
You said there's two of them you weren't doing.
Well, yeah, but
There's two of them.
what do you? I'm sorry. I'm confused with the. And in 8.8, there were. I was refusing to at the moment talk about. I mean, we can come back to these if there's time permits at the end of everything else, but where'd those stupid things go? I can't find them now. Where were they? It was 8.7, wasn't it? Oh, they were actually 9.1. So it's actually section 9.1, number 86 and number 89 of 9.1 I was refusing to do for the moment. Getting back on task here, number 38 of section 9.1, we have an is equal to what? It's equal to n minus 2 factorial divided by n factorial. And what are we supposed to do here? We're supposed to determine the convergence or divergence of the sequence given the nth term. And if the sequence converges, find its limit. So what do you guys think about this one? Ah, very good. So this is n minus 2 factorial. And this down here would be n times n minus 1 times n minus 2 factorial, right? So we cancel these guys, and we get 1 over n times n minus 1. Now, for this to make sense, I need for what? For n greater than or equal to what? 2, right. This inequality, this cancellation I just made is only legit for, in fact, the original sequence is what? The sequence, this sequence is what for what? For what n does the sequence make sense? Yeah, n greater or equal to 2, right? So that's not actually a limitation. Anyway, the point is, once you know that, what's the limit? Right. Here's a question. What if we formed a series with this a sub n? Would it converge? So that's the sum. Now you say it converges, but why? Why would that be a convergent series? Prove it to me. Because what? Sure. That doesn't prove it converges. That proves it might converge. No, that's not true. We have this series, 1 over n, diverges despite the fact that 1 over n goes to 0 as n goes to infinity. If the nth term of a series goes to 0, that doesn't tell you anything about whether or not it converges. Yeah?
Maybe by comparison to like a telescopic series?
Comparison to a telescope.
Look like it, I mean, it kind of, I don't know.
So I think I would say, I'm going to be more bold, I'm going to say this is a telescoping series. So we don't have to compare, we can just calculate. But but I think you got the right idea. Now, you were saying comparison to p equals 2. Also cool. I would do, the lazy way to do this would be limit comparison to p equals 2. Because if you look at, if we look at 1 over n times n minus 1 divided by 1 over n squared, that's n squared over n times n minus 1, right, which limits to 1. Hence, S converges by limit comparison test to p equals 2 series, right? Which is great. But that doesn't, I'm calling this thing S. If I had the instructions in the test where show it converges if possible, find its sum, this would get you partial credit, what's in the corner, it wouldn't give you full credit. To find its sum, we'd actually have to calculate we could say a over n plus b over n minus 1, 1 over n times n minus 1. And we could work out what that is and actually calculate the nth partial sum for this one. You look confused? No? You're just thinking about it? It'd take me 3 minutes to actually do that, and I know we're out of time, so I'll stop. But
So, are you going to ask us something like that on the test to be able to find?
Limits of telescoping series? Yeah,
Yeah.
possible. Yes, you should be able to finish the thought process here. That is on our list of things to do. That was probably 9.2, or maybe. I mean, this is past number 38 stopped right here, right? What's below here is me playing.
But I definitely don't feel comfortable being able to do that. I mean, like.
Right. That would be like, look, that's like